Slim, University of Victoria, who is going to talk about the relativistic Vlasov-Maxwell system in the context of plasma fusion.
Thank you very much, Tej. Thank you all for coming and attending this seminar. It's again a great pleasure to be here and seeing all these nice faces. Okay, so I'll talk about relativistic Vlasov-Maxwell system in the context of plasma fusion. So the main driving purpose of this project is to study plasma in the context of hot and non-dilute and plasma, and so this is very important in terms of applications, and to solve this problem, so we found ourselves facing another problem, and the way we will present the results today is the other way around from what we investigated. So this is a joint work with Christophe Cheveri from University of Rennes. So the plan is to talk about local smooth solvability for PTEs. And so there is a toy model given by Burger's equation. So we will test what does smooth solvability mean for Burger's equations. And then we want to move from the toy model Burger's equation to more general PDEs. And then we'll talk about what happens in the case of relativistic Vlasov-Maxwell. So what does it mean, local smooth solvability for RVL? Okay, and then I'll give a historical background I will focus on relativistic Vlasov-Maxwell, not the applications, just the standard relativistic Vlasov-Maxwell. And I'll try to see how people try to solve this relativistic Vlasov-Maxwell system. So there is a continuation criteria, and I will survey the previous methods. Specific emphasis will be given to non-resonant smoothing method, and then so how to prove the local smooth solvability for RVL using radon macro-local analysis. So this is the first part, and the second part is about applications. Okay, so let's take the very famous, very interesting Burger's equation on the real line. So we take dtu plus u dxu equal to 0 with initial data u0. Okay, and it's on the line. So we know very well that this equation can be explicitly solved using characteristics, and the characteristics are curves that the velocity is given by v. Okay, and it's quite well known that these the solution to this PTE developed sharp in finite time. Okay, more precisely, if you integrate the solution along the characteristic, so you fix the characteristic curve, and then you set v to be the derivative of the velocity on each characteristic, then this restriction satisfies Riccati type equation, which you can solve and get that solutions, they may blow up in finite time for some initial conditions. Okay, so this is quite basic, and the lifespan for solutions is given by tu naught, which is minus 1 over the mean of the derivative of the initial thing. Good. Now, if we want to do this in a uniform way, okay, so let's take a subspace of the set of C1 functions. Okay, so M is the initial data that are C1 with compact super. Okay, and let's ask ourselves, let's endow this space by a weak norm, not the Lipschitz norm, but the L-infinity norm. Okay, then So we have two norms in this space. So we have the Lipschitz norm, that's this, the standard norm, and then we have the N-infinity norm. Okay, and now let's ask ourselves, what happens if we take the infimum of the lifespan for all initial data in this large space, but instead of imposing a condition, a uniform condition on the Lipschitz norm, we impose a condition on the N-infinity norm. Okay, so only the N-infinity norm is bounded by some given upper bound S0. Okay, so we will say if PDE satisfies this, or if Burger satisfies this, then we would say it's locally smoothly solvable. Okay, so we take C1 C or C1. We don't endow this space by the natural norm, which is the Lipschitz norm. Okay, but we endow it with the weaker norm, which is the infinity norm, and we ask ourselves if we can solve in this way. Okay, good. So, so this is for the local smooth solvability, and if it is global, if this is true for any time t. Okay. Good. Now let's test this definition for Burger's equation. So we have found that for minimum, the lifespan is given by minus one over the derivative of the initial data, right? And now if we take the infimum over all initial conditions, having this upper bound, N-infinity upper bound only, not the Lipschitz upper bound, then very clearly this infimum is 0, right? Just a simple scaling. You take U0 of x, you rescale it by U0 lambda x. You don't change the N-infinity norm, but you change the Lipschitz norm. Okay. So trivially, Burger's equation is not locally smoothly solvable in this sense. Okay. Good. So now, what happens if we take other PTs? Okay. So here we are still talking about smooth solutions because we are taking initial data that are C1, right? But we supplement this by just uniform bound on the infinity norm, and this turns to be very important in terms of applications. Okay, so let's move from the toy model Burger's equation to towards more models. Okay, so I have a table here to test this notion. So we have Burger's equation. They are locally smooth in the standard way, globally smooth. But we have just seen that it's not locally solvable. And of course, it's not globally solvable. Three-dimensional Navier-Stokes Euler's equations. We have local well-posedness. And here we have local well-posedness and global weak solutions. For the relativistic Vlasov-Maxwell, so we will have positive answers to local solvability, local well-posedness. Now, what happens in terms of local smoothing? The answer is pretty much open for all cases. And the first purpose of this work is to study this notion of local solvability for the relativistic Vlasov-Maxwell. Do we have local?
I don't understand. This depends on your function space.
Yeah.
When you say absolute is not true, but
Yeah.
for example, Navier-Stokes, if you take S, HS and S there, you can propagate with 100%.
Yeah, but
so it depends which.
No. The local well-posedness is the standard.
The other one is.
The other one you have to take a weaker norm, right?
So,
Yeah, you have to. It depends on the weaker norm.
You have strong norm, but
Yeah.
you can select one critical norm which is below, and you can still get the result is positive.
I think it depends on.
If you are below the critical.
Yeah, exactly.
Yeah,
Exactly. Yeah. You want to take less derivative as much as possible, and we will see why is that. Okay. Yeah, but you're absolutely right. I have only specified the functional space for Burgers, but yeah, for each of the equations, so we can specify the functional space, and the critical one should appear. Yeah, of course. Thank you. Okay, so our purpose is really to study the local smooth solvability for RVM? And the answer is yes, it's locally smooth solvable. So talking about RVM, so let me tell you what's this system. So this is a coupling between wave and particles equations. So waves are represented by an electromagnetic field. So E is the electric field, B is magnetic field, three-dimensional. And particles represent the matter, and they are represented by a density function that depends on time, the position C, and which is the momentum or the velocity at each of the positions. Okay, so this is wave particle system. The wave satisfies Maxwell's equations. So the electromagnetic field solves these Maxwell's equations. dTE minus curl V equal to the current, and the current is the integral of mu of C. Mu of C is C divided by Japanese bracket. This is the relativistic momentum or velocity. So you integrate F against the velocity, and then for V it satisfies dTV plus curl T equal to 0. Okay, and then we have divergence free for the magnetic field, and the divergence of E has to be the total density. Rho is the integral of that. Okay, so this is the wave part. The particle part is given by Vlasov equations. Okay, so this is a transport part. Okay, and the second part is you can see it as a transport part in the momentum direction. But here, this is the nonlinear part. It's given by Lorentz force. So this Lorentz force is given by the electromagnetic plus mu cross V. Okay, and the two equations are strongly coupled because Maxwell's equation feed are fed by the density through the current, and Vlasov is strongly depend on the electromagnetic field through the Lorentz. So this is a strongly coupled system. Good. So so this combination between wave and particle has a nice properties. Okay, very nice actually properties. So we have this relativistic velocity mu of C, which is strictly less than 1, velocity of the speed of light, and this speed of light can be reached for large momentum. Okay. Now, if you define the characteristics of this system, so the characteristics, we go back here. Yeah, so this is X dot, and this is C dot. Okay, so they have a very nice geometric structure. So these characteristics, the projection of the characteristics, because the characteristics are in the phase space, 6-dimensional. But if you take the projection in X, then these characteristics, they fill the light cone. Okay, and they become tangent to the light cone when C goes to infinity. Okay. So we see that the two equations are strongly coupled, and there are nonlinearity and geometric aspects. Good. So what is our first main result? So we fix the number, we fix the size of the momentum. Okay. So P0 is the size of the momentum at time t equal to 0. Okay. So beyond P0, the density is 0. Okay, and then we take the space of C1 in terms of density function and C2 in terms of electromagnetic field. And we suppose that we have the support of F0 is in terms of momentum is bounded by P0. Okay, we are not taking the natural norm of this space, we are taking somehow a weaker norm. Okay. So what is this weaker norm? So we take an infinity norm for the density, so no derivatives. And when we take the energy norm, okay, so you can think about this space as H1 cross H2. You can take P equal to 2. Okay. So we call this norm is small norm or weak norm. So this.
So, Steve, when you call it energy norm, I mean, that energy means just the NP norm.
Yeah. Yeah.
H1 on E and P.
Yeah, exactly. Yeah, but
It's not
yeah,
energy.
you're right.
It's one, but it's-
Yeah, you're right. Yeah, I call it energy. Yeah, you're right. Right. We'll come back to this. Okay, so for this,
Sorry.
yes,
Is there any scaling dividend of this system?
I think it's a coupling, so I don't think there is a scaling. Yeah. So the pioneer result about this this system goes back to Vlasov-Strauss. It's a pioneer work. It's beautiful, but it's very complicated, really very complicated. So they show the local wave positiveness in this space with the C1 norm for the density and C2 in the electromagnetic field.
To understand more, so this norm is very weak. So can we at least construct a solution with this norm, or?
You can construct weak solution even with weaker norms.
And this is general for this framework when we have. So if we have this responsibility, so we can construct a solution with this weak norm, or it is not clear?
No, it depends. No, it depends.
If you approximate your data by
Yeah.
your data, so
You get weaker solution.
at uniform time.
Yeah.
It's not, but the question is to compare this to
No, you can construct weak solutions via this procedure by approximating the initial data. But does this apply to every equation? I'm not.
So that's my question about the weak norm, how to fix your weak norm. Because
No, you're right. I mean, as I said at the beginning, we didn't start by doing this. What motivated us is really the application. Okay, and for the application, we really don't need to take derivatives for the density. As long as we take derivative, we can do anything. Okay, so this is so weak norm. There is no like standard weak norm, but for us, so we were debating we should call it small norm or weak norm, because there is a controversy. But for us, no derivative or the least derivative that you can take, okay, from the standard wave positiveness result. We would call this like a weak topology or small topology. Okay, is that clear or not? Yeah.
The finding essentially connect to this weak norm.
Exactly. And even for the standard wave positiveness, so what we will show is the lifespan for the standard wave positiveness will be lower bound by the time of this week. This is exactly our purpose. This is exactly what our purpose. Exactly. Yeah, exactly. So this is exactly. This is exactly our purpose, is to show that the local wave positiveness in this space, that the lifespan is lower bound by the local wave positiveness if we take this weaker norm. And we are calling this weaker norm because we are not allowing to take derivatives as much as possible. Okay. So this may be like a mathematical result, but it seems like it's related to turbulence. And in turbulence, we have like coherent structures, which is manifested by cascade of scales, or filamentation, which is the shearing. And this be more specific here.
What do you mean by turbulence? I didn't understand your turbulence.
Yeah, I'll talk about that. Okay, because in the application, so we will take very oscillatory systems, and characteristic can be very wide. Derivative can be very wide, but the size you can control it an infinity amount. Okay, so let's take the basic pendulum problem. So the phase portrait is very nice. We have a sequence of stable and unstable equilibrium points, and we have these famous separators, right? The red ones that separates the enclosed region and the outside region. Okay. Now, if you take the story of cats, so if you take a cat inside the parametrics, separatrix here, and you let it flow, then what happens here is coherent type structures. However, if you take the cat in the outside, then you do see this stretching. Okay, so these are the two phenomena that I have, and in practice, this shearing you can see it in Aurora, in the north region of the globe.
This has to do with the fact that the plasma cannot go in the lines of the magnetic field, cannot go through it.
Yeah, I think this is.
Usually they have a rule that the plasma cannot go through the lines of the magnetic field. That's why they stretch.
I think this is like more confinement. Yeah, this is like more confinement.
Yes.
Yeah, exactly. Okay, so let's go back to Placé-Strauss criteria about continuation. So if the Ritchie's norm of the solution is infinite, that means that the momentum has to be infinite in finite time. Okay. Good. So P of t, this calligraphic P, is the infimum of the size of momentum beyond which the density is zero. And the main idea, or the main step towards this continuation principle is to try to find bounds like this on the size of the momentum. Okay. If you can make estimates and you measure the momentum at time t through the momentum at time 0 plus the integral of some weight function times the size of the momentum to some power, then you can claim through Grunwald type inequality of Bihari-Lassab that the momentum remains under control on the time 0 t. Okay, so this is the whole game is to get an estimate like this.
So, but that depends on what is n or n.
I mean, as long as n is not 0, then yeah. I mean, it should be more or less.
But this can lead to blow. If you have something like this,
I think it depends on the weight.
yeah, it depends. But like something like this is typical of things that can lead to blow.
Yeah, but yeah, I think the weight is really important here. Okay, so in order to get the size, the control of the size of the momentum, so we'll define the momentum increment. So what is the momentum increment? The momentum increment is, so we want to really to measure the size of the momentum, right? And the momentum spreads with characteristics, right? So let's take a characteristic. This is a characteristic that at time 0 starts from a point y with the momentum eta. So we follow the characteristic at time t, so it gives us this, minus the value at time 0. So this is exactly an increment, okay? Because the size of the momentum at time t minus the size of the momentum at time 0. And this is the thing that we need to control in order to control P, which is the supremum, right? So P is basically the supremum of all the momentum increment. Okay. So what is the dynamic of this momentum increment? It's very, very easy. So the momentum increment is the integral of the derivative, right? And the derivative using the characteristic equations is given by the integral from 0 to t of this mu at the characteristic c dot with the electric field. So
I don't understand what is E of R is what?
R is a variable, like
R is time.
yeah, it's like fine. Yeah.
So just integrate with time.
Yeah, just integrate. Okay. So what is contributing to this momentum increment is exactly the electric field. Okay. You see, from here, what is contributing is the electric field. It's almost true. It's not true. It's almost true.
In bracket, it's the average.
No average. Sorry, no stochastic. This is Xi. This is Xi. The Japanese bracket.
Yeah,
Japanese,
velocity.
Yeah,
Square root of one.
square root of 1 plus C squared. Sorry. Okay. Now, given that this relativistic velocity is always less than 1, right? So controlling this, if you can control E, then you are done. So let me explain exactly what are the techniques to do the control of this momentum increment. So we can summarize the techniques into two, maybe three techniques. Okay. So the first one is brutal, right? The first one. This is less than 1. So you integrate from 0 to t, the electric field. If you can control the infinity norm of the electric field, you get t times the infinity norm of the electric field, right? This is the brutal one. And this goes back to Wallman, 1984. So this is controlled by that, but now you need to have bounds on the infinity norm of the electric field. Okay? But the electric field, the electromagnetic field solves wave type equation. So it solves Maxwell's equation. And wave, they act very badly in the infinity space. They are not well posed. Okay. So what people do, take more derivatives, right? Maxwell's equations are not well posed in an infinity, but they are in L2. And then if you take enough derivatives, then you can control HS, norm of E. And if you control enough HS norms, then you can control L infinity norm. Okay. But taking more derivatives in the electric field, let's see what does this give us. So this is Maxwell's equation, right? So asking that this is in HS with S large basically means that the density has to be in HS with S large. Okay. So that means that we need to take derivatives on the density function. Good. But this approach, you can prove local well posedness in HS S large with a time of existence that depends algebraically on the size of the initial data in HS. And by doing this scaling argument that I explained at the beginning, you can show that this does not give us local smooth solvability. Okay, so you can make this increment to be 0. So this is the first approach. The second approach is you want to do dispersive estimates. So this approach by Kleinerman and Stapilani in early 2000, I think. Okay, so the moment increment, you can control it by relativistic velocity, which is less than 1, you throw it away, and then the integral of 0 to t of the infinity norm. And then you say, okay, let me try to use dispersive estimate for the electromagnetic field. Okay, but the dispersive estimate it gives you L2, not L1, and this L1 and infinity, it's like at the borderline and can't be done. Okay, so we are basically in trouble. Good. So the third approach, which is nice, is due to Bouchy-Girard goals. And the idea is the following. So it's a really very nice idea. So we want to avoid derivatives on the density function as much as possible. Okay. So they introduced this scalar function, which is called the linear Wishart potential. It's scalar potential. So it's the inverse. U is the inverse of the non-Gaussian inverse of the density function with zero initial data. The advantage of this potential function is that you can rewrite the electromagnetic field through this potential function. Okay. So you can rewrite E and B in this way. But this way is not very convenient. Why? Because we still see derivatives on U, and the derivatives on U means derivative on M. Okay. So their idea, a brilliant idea, is the following: to overcome this one loss of derivative. So this potential function, U, this scalar potential function, it satisfies the wave equation. So U can be rewritten as the fundamental solution of the wave equation, which is Y, which is a distribution convoluted with F. So this is the linear Wishart potential. Okay. So Y is this distribution. Okay. Now the idea is the following. Okay. So we want. Let me go back. Sorry. So we want to rewrite dt derivatives of U, this dt and grad x, in a different way. Okay, they want to rewrite it in a different way. Okay, so what they said. So this is the cone x equal to t. Okay, so let's take a slope that is transverse to this light cone. Okay, so let's take A. A is a function with less than 1. Okay, and then the x derivative, for instance, can be rewritten in this way, right? This is triggered. And then if we apply this to the light cone, if we apply this to the light cone, this is tangential to the light cone, so this goes away. So this dx applied to delta is nothing but this applied to delta. Okay, and now they want to commute this one. They want to commute it with the derivative. So that you want to put it outside, inside. So let's do that. So dt plus 8x, you can commute it. So now the multiplication is inside. And then you have this multiplication factor that comes out. Okay, so this is very, very simple.
Oh, yeah, because A is
Less than
function.
yeah. Yeah. So this is transverse. We are taking.
And then we're going to replace the function A with the C.
Yeah. So now you want to replace. You want to have Vlasov derivative. This is Vlasov derivative. Okay. So the fundamental solution, the derivative of the fundamental solution, you can rewrite it as the Vlasov derivative plus multiplication, right? Now, this is important because U is what? It's the integrated form of the t and x derivative, right? And integrated form in terms of xi. And now you replace it. This derivative by this Vlasov plus this multiplication. Okay. And then what is the advantage? Since we are integrating, U is an integral in C, so you can put the derivative on the density F. Okay. And if you do that and you use that F solves Vlasov equation, then you get something like this. So now we can represent U, we can represent the electric field not in terms of the derivative of F, but in terms of Lorentz force times F. This is nonlinear. Okay, and the derivative, loss of derivative has vanished. So this is really a beautiful idea due to.
I'm still confused, but in step 1, we still have this Vlasov derivative.
Yeah, yeah.
Right.
But U is the integral. It's right?
But U is the U, so you gain as the derivative.
Yeah. So you can put the derivative now, you integrate by parts, you can put the derivative on F. It was on Y, on the fundamental solution, right? You put it on F, and on F you use Vlasov, which is this, right? So the loss of derivative disappears. So no more loss of derivative. So this is, these are basically the three.
This allows them to prove what?
This allows them to prove the local wall positiveness. It's still local wall positive, nothing more, but it's a different proof, different,
For the electric field in
more
LNFD.
geometric proof. Sorry.
For the electric field in LNFD. Because at the start you couldn't control the LNFD volume. Right?
Yeah. No, but it's the thing is you take like C2 in the electromagnetic field. Yeah, and then you can control the infinity norm using this. But it's still local wall positiveness. Still local wall positiveness. I mean, to confess, like Glaser-Strauss result, it's really very complicated. I mean, it's beautiful, but to read and to follow, it's really very complicated. And this method, it's beautiful because it uses like the geometric property of the system. Okay, so we will propose like a different way to control this moment increment, and this way is through Radon transform. Okay, so the Radon transform, I don't want to spend too much time here, but the Radon transform is more or less like Fourier transform. You take it in radial coordinates. Okay, so you have f hat of xi, and xi you write it as r omega, but here you symmetrize r. It's not only positive. You can symmetrize it r positive and r. So more or less this is the Radon transform. I think I will skip this part. Okay, so you can think of Radon transform as Fourier transform. Okay, so you have Vlasov, you have the transport. F is a function of the physical variable t, x, and c. You apply Radon transform, you get a function of t, the Radon transform in x. So the derivative in x becomes omega, which is the direction, times dp. Okay, so derivative in x becomes derivative in t, p is in r. Okay. And then s becomes Radon transform of s. Now, what's the advantage of this? So starting from wave equation, three-dimensional wave equation, you get one-dimensional wave equation. Okay, so the omega, the direction is just a parameter here. Okay, so from the three-dimensional wave equation, you get one-dimensional wave equation, and then you want to invert back, right? And when you do so, you need to integrate over the domain of dependence, and then you can recover V by integrating over this domain of dependence, because we know how to solve, or we know how to explicitly solve the one-dimensional wave equation, right? And then we need to invert. Okay. So after this computation, so we take Vlasov-Maxwell system, we apply Radon transform, and then we invert it back. And if you believe me, so this is what comes out of the momentum increment. Okay, so you get 6 integrals, right? And now integration is over r, which is time, x is space, c, and omega is the direction, the space. What is crucial here in this derivation, we have a multiplication by rho square, and this the multiplication by rho square is like the multiplication by c square in Fourier. In Fourier, it represents the loss of 2 derivatives. So we need to get rid of these two derivatives. Okay, so we will do this through non-stationary phase, basically. Okay, so the first one, it's almost trivial. So when we integrate over the sphere, this integral with the phase, then we can take that. So this is non-stationary phase. Okay, so instead of having 6 integrals with this integration, we get 5 integrals. The second one is more geometric. So here we have we take a phase. So the second integration by parts, if you want. So you see that if you apply Vlasov vector field to this phase, then you basically get this, but you need to divide it by this factor. Okay, the derivative of the phase. And we know that this is not zero because the relativistic velocity is strictly less than 1. Okay, so there is a micro-local ellipticity here that plays role. Okay, so second integration by parts. Yeah, no, you will get. Yeah. We didn't get rid of infinity. There is this problem. Yeah, but for every fixed xc, you can do this, right? Good. So, so after this integration by parts, I think I skip this. So we get our representation of the momentum increment. Okay, now we started with 6, but we ended up with 4. Okay, now what is important here? So we have integrations with respect to s, which represent the time, and the omega, which is the direction, and c is the momentum. Okay, and you can see this as a dynamical equation. Now we want to use the fact that we have a divergence-free vector field, so it's a volume preserving, and this map here is a diffeomorphism, and we can calculate exactly its Jacobian. Good. So you may have a shearing, and you may have cascade of scales, but the measure is volume preserving. Good. Now, what is our driving idea? So now we have kind of representation of this momentum increment. Now, our driving idea is not to put derivatives on the density function f. Okay. Okay, so we have the momentum increment, which is represented in r, s, omega, and xc. But what we want to use is we want to use conservative quantities and no derivatives on the quantities. So what do we do? So we can change variables to go back to the original variables, x, right? And by doing so, the norm that we want to appear on E is the energy norm. On E or on F is only the energy norm, okay, which is constant. So after some calculation, we want to get something like this, okay. So this is the idea. So let me explain. Let me do a quick recap. So we have Vlasov, right, coupled with Maxwell's equations, right? And then we wanted to show the existence of solution on the time that depends only on an upper bound of this law. Okay, so as I said, the main thing is the momentum increment. Okay, so now let's implement and see how we get this result from the control of the momentum increment. So let's define Q of t, the size of the support in X, in the X variable. Okay. And since the X dot is given by nu of C, and nu of C is less than 1, so the X propagated velocity at most 1. So Q is always controlled by the size at time 0 plus t, propagates at most 1. Okay, and then similarly, we want to define the size of the momentum at time t by this increment. Okay, and the main thing is we want to control P of t by Grunwald type equation. Okay, so the theorem, the smooth solvability will be a consequence of this proposition. So we fix the initial size, we fix the supremum as 0, which is the supremum of the density function and the electromagnetic field. And then we can construct a function, an increasing function f, that controls P on the time existence given by the local well positiveness. And moreover, if the data is small, then the solution exists for a long time. So how to do that? So how to do that, as I said, so these are, again, the characteristic equations. The density function can be integrated along characteristics, right, through the initial density. And the momentum increment is just the difference between the size of the momentum if you follow one characteristic minus the size of the momentum at time 0. Okay, so this very complicated formula that I showed you, it leads to the decomposition of the momentum increment into the following terms. So the momentum increment can be decomposed in 4 types. So the first type, it's dictated by the initial density. So that's the contribution of the initial density on the momentum spread. The second one is the contribution of the initial condition of the electromagnetic field to the momentum spread. So EH solves linear wave equation with the initial data of the electromagnetic field. So this is the influence of the initial data, the initial electromagnetic field on the momentum spread. The third one is a linear, because you see only F here. W here is a weight, W0, Wn, these are weight functions. And then last contribution comes from the nonlinear term, which is given by Lorentz force times F. Okay. Okay, so this is an identity that really localize the influence of each component of the system. So the component of the system are given by the initial density, initial electromagnetic field, and by the linear and nonlinear contributions. And as I said, these weight functions, W0, W1, Wn, these are explicit weight functions. So for instance, this is W0, W1. So our strategy is to get a nice estimate about these weights and try to appear as much as possible conservative quantities. So we have few complications, as you mentioned. So we have singularities that comes from Xi large. So Xi large, then the relativistic velocity can go to unit direction. So this means that we have singularities that we need to handle. There is another singularity when we want to go from random coordinates to the original coordinates, x coordinates. So we need to apply the Jacobian. So we need to apply inverse power of the Jacobian, and inverse power of the Jacobian will manifest on singularities in time. Okay, so this is singularity in omega. These are singularities in time, and we have similar singularities when we apply the inverse power of the Jacobian back along the characteristic. So these are the things that we should keep in mind. And we do this through following lemmas. So we can control U of C, and so this singular power, it costs like eta square at the most. But when you integrate it over the sphere, you have some gain. Okay, so you have delta gain here. And when delta is 1, it's like log, and if delta is less than 1, then this is uniformly bounded. Okay, so let me show you, or before showing you how to do this, how to implement this. So let me show you that there was one weight which was weird. So this is the weight that was weird. We have the derivative, but we decompose this into 3 directions, 3 almost orthogonal directions: the omega and omega along the characteristic, nu along the characteristic plus omega, and so on. Now, if we combine these explicit formula for the weights and the lemma, these technical lemmas, then we can get this nice type of estimates. Okay. Good. So let me show you how to estimate one of the terms. Okay. So D0 is the contribution of the initial condition of the initial density. Okay. So that's why you see F0 here. Okay. So what do? We want to use conservative quantities, right? And we want to use conservative quantities, but the conservative quantities are given through X variable, not the omega S variable. So what do? So we appear the Jacobian here, and this is almost the Jacobian. So this is 1, right? And then we want to use the energy. So we appear C to the power 1p here, and C to the power minus 1p here. Okay, so I did nothing here compared to the previous slide, except I'm preparing the framework that we are going to use. Okay, so what do? Holder inequality. So we take this to the p power. So this gives us energy term. So this is F0 to the power 1 over p and the rest. So the 1 over p gives me the energy term. The other one, F0, is less than an infinity normal to F0, right? And then we are left with this weight now. Okay, the integral of this weight, and this is somehow explicit computation that we can calculate very explicitly. So as you can see, we can estimate the momentum increment, which measures the size of the momentum by conservative quantities. So E0 is the energy, S0 is the infinity bound of F0, no derivatives here, right? And P0, which is the size of the initial momentum. Yes. Sorry? Because you have omega here. Yeah, I think the radon transform is somehow Fourier. Yeah, it's sort of polar coordinates of Fourier. And you can see that you have these singular weights, and you really need to distinguish about two frequencies. Okay, now let me show you another example how to estimate the increment, the momentum increment given by the initial electromagnetic field. So the initial this increment is given by this, right? So EH is the solution to linear homogeneous wave equation, but with initial data, the initial data given by E0 D0. Okay. So we were able to estimate using again the energy and infinity norm. And if you remember from the techniques that I told you, this term is like one of the most problematic terms. For instance, if you take initial data in the energy space, H1, it's not clear, it's not at all clear that this makes sense, because we are integrating the solution to the wave equation along the curve. Okay, so a priori, this does not make sense for initial data independent systems. However, using like this volume preserving map, diffeomorphism, then we can make sense of this and we can estimate. So more precisely, so the homogeneous the equation, the solution to this wave equation, it's given explicitly by this formula. So M is the average of the sphere. And then we repeat the same game. So here we have integral over the sphere and integral over the time, right? And then we want to change variables to go to the x variable using this diffeomorphism. So what we do, we multiply by j and power of j, and we divide by power of j. So this term can be controlled, right? And then we are left with a singular integral that we needed to calculate. And using our previous lemma, so this computation is explicit. Okay, so this contribution here, it may seem linear or coming only from the initial condition, but this is not true. Okay, this is not true because we are integrating the wave equation along the characteristics, and the characteristics, they see the whole system. They see the whole, the full dynamic system.
I have a message.
Sure.
Thank you.
Yeah. Oh yeah, we should have put it here. Yeah. Okay. So maybe we can stop here. Yeah, I think we can stop here.
Couldn't understand correctly your like this. So you say that we start need to it up.
Yeah.
Without that there are
Yeah, exactly. Yeah.
And what the point saying on us is that you can relate what less fun
Yeah, exactly. So yeah, you may have a lower bound of the lifespan using weaker bound. Yeah, exactly.
But I think the point that the block criteria is related to the support, not to the main.
Yeah. And that's it. Sorry. Yeah.
I have a question. What
Let's,
happens if you don't take compactly supported initially?
in
Think about the support
in-
that
in X or in XC?
you see.
In XC, yeah, I don't know. Yeah, I mean that's it. Yeah.
There is no.
I think you can. I mean, you can do something. Yeah, I think there are results. Yeah, when you can remove this.
Because the one thing about this is the fact that you start compactly supported.
I don't think that's the difficulty.
Because if you're not